First, so this is actually equation of continuity. I actually thought to share. It actually just help make the work easier. So this is from the slide on equation of continuity. So one thing you have to know, equation of continuity has to do with how fluid can sustain same volume after being transferred from one medium to another, from one column to another, something like that. Sha. I'll just explain briefly. So now on that medical physics, one of the things that I said here is we're talking about fluid, right? So what our major concern for medical field is actually fluid flow. We cannot know fluid flow without knowing what is fluid. That's one reason why I decided introduction of fluid. Basically, it's a substance that flows, and they started defining fluid in terms of the shear pressure too. Fluid does not support shear pressure and the likes. So they now said something about fluid in terms of classification of fluid. There are two types of fluid: we have the compressible fluid and the non-viscous fluid. Then the ideal fluid was given to be incompressible and non-viscous. So these are some notes to just take note of. The ideal fluid is incompressible, so IC, and non-viscous. That was said to be the ideal fluid. Then, knowing about fluid now, we can enter current. I was thinking, because reading, I was like, how am I going to get entrance into this medical field? It's looking boring. But why are we doing medical fields as a medical laboratory science? It's not because you want to ask yourself, why we are doing medical fields? But I've not really gotten the entrance into everything, like one of the reasons, but I want to medical reasons because I think with fluid. And this fluid, there's no hours in medical practitioner that you don't need to know the, you don't need to know about fluid. Because if you are checking those, you see, Bono, I don't need to spell this correct, this law, we are checking it. There's a point where the the vessel in which the fluid is passing through can be like this. And seeing this picture, seeing this image just take me straight into vein. The normal vein was ought to be straight, but in a situation whereby atheroma, so whereby fat is accumulating in the vein, so the vein now comes like there is reduction in the size. But even though there is reduction in the flat size, if the fluid is perfect, the fluid is hygiene, obviously there will not be reduction in the flow. So that's one reason why I'm learning about this fluid. That okay, what will happen if this fluid like this? So what's my type is probably either the pressure, it might change the pressure, but the volume does not increase. So our concern here now is this like equation of continuity. So after knowing what energy field is, obviously, then there's something like we call current. So current in fluid is almost the same thing as current in electricity. It's almost the same thing. Current in fluid is equal to the mass or volume of the mass of volume flowing through a cross-sectional area with a unit time. So it's kind of like the mass of volume, either of the liquid or anything, as long as it's a fluid flowing through a cross-sectional area in a unit time. So flowing through the side in a unit time. So that is current. So now talking about equation of continuity, there's this diagram that is on that PDF. So what is the diagram? This is the diagram. So if we are being asked, I think this will just be an easy show. So just give them something like this. So what are you interested in? Like interested in the area. So cross section area. So that's kind of like maybe circumference. Then why are you so interested? You're interested in the. So I'm using this pen for velocity. Then so this is distance. What again are we interested in? So this is velocity. Remember, we're using this pen velocity. So this might not be exactly how it looks like in the drawing, but I told you something. Then see. So first, the one point to note is that you have to start your derivation. You have to derive equation of equity. You don't have to start your derivation with the fact that this is incompressible. Now incompressible fluid. Remember, we already stated that incompressible fluid obviously does not have incompressible fluid obviously an ideal fluid, sorry, is incompressible and non-viscous. So now this is incompressible, so it's kind of like an ideal fluid. One reason why, how do you know if a fluid is compressible or incompressible? The thing is that if you put a fluid in, you cannot press it to know if it's compressible or incompressible. So it is doing the movements you can tell if the fluid at this place measures a density of maybe 60, and at this place measures a density of 53, because there's like a collapse in the medium into which it is to measure the density of 40 or so. Now it's said to be compressible, but if not, if it still measures same 60 diameter, then it's incompressible. So that's how you know. So there are some gases. Gases are obviously known to be compressible because at different medium they weigh different density. But there are some gases that are incompressible. That is if from the slide, they say if the speed of the gases is around the range of or below this, so 50 meter per second. So if the speed is below 50 meter per second, then the change in density will be insignificant. Then it can be considered incompressible. So back to incompressible fluid, back to this. So these are just bonus points. So first point, so let's assume that the fluid particle move in parallel motion. I don't want to write because of time. Let's assume that the fluid particle move in parallel motion with equal velocity v. So it's moving parallel motion with equal velocity. So that's the first point. That's the first point you have to assume. So the second point is that let's assume that the time change in t to get to a distance s. So using s as a distance is equals to, and this is from v change in t. Remember v is velocity. So this is not something far-fetched. Then third is now considering that this is a fluid flow. So now the change in volume, so I'm not using this for the change in volume that pass through a cross-sectional area is going to be equal to AS. I know from obviously the unit of volume is equal to centimeter cube. The centimeter cube now, A is area, Abina. Then times x. X is distance. So this is it. So this is what we have already. So now change in volume is now going to be A, substituting what S is, so dot V, then change in T. So this is what we have already. So now from recalling current, remember I did this formula for current. So correct formula from PDF, D dt. So now this is going to substituting this into it. So now the T now we're using change in T. I'm changing V instead of dV. Plus to change in T. Then so because you are substituting this, so it's going to be equal to A dot V. So V, that's more beta V, color V is tend the velocity change in T. So papa, so we either have this AV. So this is just an entrance. This is not like BD. Like this is just an entrance, obviously. So this is what we have now. So at this point, we are okay. Velocity and volume is actually constant and not changing. Then you have to start deriving the formula. You have to draw this stuff. So this is also from the diagram. Don't mind my drawing. Then this. Oh my God, this pen is failing me already. Why? Okay, I'll just use green. I'll just continue with green. This. So the aim is for you guys to understand. So that's the reason. So at this point we have t equals to 0. At this point we have t equals to change in t. At this point we have t equals to 0. At this point we have t equals to change in t. So this is A, this is M2, A1. A2, sorry, A1, M2. So now we're talking about velocity 2, velocity 1. We're talking about, so there are some things to just note. So as we go further, x is now equals to what is s? S equals to v change in t. Then what else? So we're waiting the A. So this point now we're labeling it 1. This point we're labeling it, sorry for the wind. Let's come and let's see this stuff. Okay. So now we're labeling this one to 1. This point we're labeling it 1 with this. Then this point we're labeling it 2. So that one we're labeling it 2. So the point we are labeling is this change, obviously. Because of time, just trying to watch it. So continuing. So now after noting all these points, so remember this is not the equation of continuity. But you have to start with this. I think this just give understanding. And you can be writing those stuffs. This is actually in the slide, but so it will just be easier. So after writing this, so what is next now, right? So now there's something to take note of is density. So density equals to mass over volume. You might not write this on there, but it's just something that will guide you. So first we're talking about the mass. So now talking about, so now let's say number 1 or bullet. So those 3 points is bullet. So number 1, mass, the mass from this point, so the mass from 1 and 1 apostrophe this, then or and 2 and 2 apostrophe this is equal. No, sorry, first we're talking about density. So density at these 3 points is actually equal. So density for 1 is equal to density for 2 is equal to density for 3 is equal to density, normal density. That's the first point to state. Then second point is talking about the mass. So the mass at this are equal. So mass of 1 is equal to mass of 2 equals to mass of 3 are equals to mass. So then the third point is we're talking about volume now. Is it volume? No, we're talking about yes, volume. I'm talking about changing volume. To change the volume at this point is equals to AS. Remember from what we did here. That is why I said this place will actually help you. Change the volume is equals to AS. So now change the volume for 1 equals to AS1. So now change the volume for V2 equals to A. This will be A1 S1, A2 S2. So now change the volume because it is incompressible. So at both points, so this is the entry of the liquid, this is the point at which it leaves. But at those points, the liquid is set to be compressible. So it still has the same velocity, a bit same volume. So this is V2 equals to change in volume. So now let's now substitute for S. What do we have for S? S is velocity change in T. So now coming here to substitute for S. So it's going to be change in V1 equals to A1 V smaller than V change in T. So smaller than V1 change in V2 is going to be A2 smaller than V2 change in T. Then remember, since change in V equals to this, so obviously A1 V1 change in T equals to A2 V2 change in T. Change in T to cancel change in T. So A1 V1 equals to A2 V2. So since A1 V1 equals to A2 V2, so this is the this is where we stop. It be like the this is where we stop for the equation of continuity. So on the average, this is constant. This is the major point. So now then we can write something like AV is equals to, since AV is equals to 1. So this V is actually velocity. Yes, it's actually velocity. So since AV is equal to 1, then it means volume is constant. So for in summary, the equation of continuity states that even though if the liquid is incompressible, even though it moves from one medium to another, the volume will obviously remain constant. That is summary of it. I just hope this was helpful. At least to get it. Thank you.